Welcome to episode 2 in the DogBot series. In this episode we'll be going over the mathematics of the DogBot. Now if you don't like mathematics, it's okay, because I'll be giving you the answers. And if you love mathematics, I'll be telling you where to pause the video so that you can come up with the answers yourself. The first element of mathematics that's found in the DogBot has to do with the golden ratio. Now, a long time ago, mathematicians decided that some of the beauty that's found in nature has to do with what they called the golden ratio, which is a number 1.6. So I decided to incorporate that number into this robot in two ways. First, the distance between this drive shaft and the tip of this leg is exactly 1.6 times the length between this drive shaft and this drive shaft. In other words, the length of the lower leg is 1.6 times the length of the upper leg. And also, the length of the robot is 1.6 times the width of the robot. The second element of mathematics that I wanted to talk about has to do with the leg's coordinate system. And I decided that instead of thinking in terms of angles, these three angles for each leg, I wanted to think in terms of a three-dimensional coordinate system, x, y, and z. In other words, what's the position of the tip of the leg in relation to where the leg hooks into the body? It'll be easier for me to explain if we move over to the computer. So why don't we do that? Okay, so we're going to be using MathCast for all of our equations and OpenSCad for visualizing. They're both open source applications. Alright, so we have our leg here. And the first thing we need to do is establish what we know. We know L1, 2, and 3 because we designed the leg. We know the length of the lower leg, upper leg, and the radius of the hip joint. Alright, we also know x, y, and z because we're giving those as the parameters into the leg. So just as an example, we can vary y, and we can vary x, and we can vary z, and we can watch the leg respond to the different values. So we know x, y, and z. What we don't know is a, 1, 2, and 3. And that's what we're going to be solving for here. So now's a good time to pause the video if you want to solve for a, 1, 2, and 3 on your own. Otherwise, we'll do it together. Alright, so the first angle we're going to solve for is a3. But before we can solve for it, we have to define a few more values. So looking at x and y, we're going to create a variable u. And we're going to solve for u using the Pythagorean theorem. So u squared equals x squared plus z squared. Therefore, u equals the square root of x squared plus y squared. Alright, so now we have u, and with u and z, we can define a new variable, p. P is the distance between the first drive shaft and the tip of the leg. And just like we solved for u, we can solve for p. Alright. Now with p defined, we can solve for another variable called k. And to solve for k, we need to bring L3 into the mix. And k is the distance between the second drive shaft and the tip of the leg. Alright. So with this equation, it's going to be a little bit different because we have to first, actually, k, there we go. We have to first refactor, so it's going to be k squared equals p squared minus L3 squared. So k equals the square root of p squared minus L3 squared. Alright, so now we have k. And with k, and if we bring L1 and 2 back in the mix, we have a triangle with a3 inside the triangle. So since we know L1, L2, and k, and given the law of cosines, we can find a3. So the law of cosine says that k squared equals L1 squared plus L2 squared minus 2 L1 L2 cosine of a3. So now we need to refactor a little bit so that we can solve for a3. So first we're going to put a3 on one side of the equation, everything else on the other. And then we're going to divide by 2 L1 L2. So actually, why don't we copy and paste to make it a little bit faster. Copy, paste, copy, paste. There we go. Alright, so now all we have to do is take the arc cosine of both sides, and so now we have A3 equals arc cosine of that. Okay, so let's make it blue because that's one of the 3 equations we need to solve for. Solved. So now let's solve for A2. But before we do that, we need to define a few more things. So A4, let's define A4 as another angle in this 3-sided triangle that we've been using. And again, just using the law of cosines, we can quickly solve for A4 the same way that we solved for A3. Alright, let me just type it out here. So now we have A4. There we go. And we also need to define A5. Now to solve for A5, we're going to have to bring in y into the equation. Alright, so now we have a 2-sided triangle that we know the values for. We know k and we know y. And we're solving for angle 5. So A5 is going to be our cosine of y over k. Alright. Now, with A4 and A5, we can solve for A2. Let's bring the leg back in just to see where we are. Alright, so A2 equals A5 minus A4. So now we have 2 of the 3 equations that we're solving for. And finally, we need to solve for A1. Before we can solve for A1, we have to first create another variable called g. And again, we can just solve for g the same way that we solved for p and for k and for u. So let's just take the square root, and we get g equals the square root of z squared plus x squared. Alright, now with g, if we pull L3 back in the mix, there we go, we can solve for A6, which is another angle that we just created. So A6 is going to be arc cosine of L3 over g. And finally, we need to define one more thing so that we can solve for A1, and that's A7. So A7 is going to utilize g and x as 2 sides of the triangle. And so we can solve for A7. Here we go. So A7 equals arc sine of x over g. Alright, so now with A6 and A7 we can solve for A1. A1 is just going to be, let's see, A1 equals A6 plus A7 minus 90 degrees. Alright, so we have all 3 equations, A1, 2, and 3. And obviously the equations are already built into this OpenSCad application. And so we can do cool things like we can vary z, and we can watch A2 and A3 change as z varies over time. Very cool. And we can also, we can add in x, we can vary x at the same time just to make it more interesting. And now we say A2 and A3 and A1 are all changing in response to z and x changing over time. Very cool. So we're done. Keep an eye out for the next episode, where we'll be taking one more step into turning this virtual robot into a reality.